lecture. So thank you for coming back. Just as we were talking about getting to campus, so I did have my COVID test last week. I don't have the results yet, but since faculty and staff are returning to RIT before the semester actually starts, we've been permitted to get our tests. I think it wasn't as bad as I thought it was going to be. You know, I'd heard a lot of people say that it's painful or whatever when they stick the thing up your nose. It kind of was. I don't know if anybody here has had it before. It kind of, to me, felt almost ticklish, but really sort of deep in your sinuses. So like where you couldn't get at it. When it was happening, I know my eyes were kind of, blinking and watering a little bit. But it was 5 or 10 seconds. I wouldn't say that it was comfortable. It was probably uncomfortable, but it wasn't too bad. Here in Rochester, you can get it done free at MCC if people are there. You fill out a form online, and then they get back to you with a schedule, and it's kind of a drive-through thing, and you open only, you stay there with your windows up, and you sort of only unroll your windows when you do the test. So I don't know if that's helpful for anybody, but I thought I'd share my experience. Does anybody else? I know Jack had a question about coming back, which I unfortunately didn't know the answer to, about how sort of the dining services will be running. Does anybody have questions about kind of returning to campus in the fall? All right. Well, if you do, and Jack, I'll pass your question up to our department head too to see if she has any information or can point me in kind of the right direction too. And if I get that information, I will share that with us next class. So today is the last class with new material, and it's new material in that we'll be doing an example of the a heat pump cycle, which, as we learned last class, is essentially the same as a refrigeration cycle. The difference is our energy benefit. So whether we're interested in cooling down the cold place or heating up the hot place. And then after this class, we have 2 more classes this week, which I've reserved for course review. And then also 2 classes next week because the semester doesn't end till Wednesday. So we have a total of 4 potential review lectures. So my idea for the first review lecture is I have maybe 10 minutes of content to share, just kind of a general overview of how to do cycles. But then I'd be interested in having students, maybe look through the textbook or something and sort of pick a cycle type that we can go through and sort of go through an example together. So something that I haven't seen before, you can kind of ask me the question and I'll go through the problem showing you how, the method that I would use to go through to solve it. So I think in 2 slides, we'll talk about maybe which different cycles we can look over and if people have a preference of which cycles we can do on which days. But before we do that, I also would like to, so today is August 3rd, Monday, right? So we have all of this week and then half of next week until the end of the semester. And then we will have our final exam on the 14th. So that's the Friday. The final exam will consist of 10 multiple choice problems, just like the midterms, but then 3 long answer problems. So an extra long answer problem versus the midterm exams. And you can certainly expect that these different long answer problems will ask you questions about the cycles that we've been going over really since the second midterm. So in the midterm exams, we ran the exams from 3 to 7 because there's an extra exam problem here. I've extended the time by half an hour. So we'll go between 3 p.m. and 7:30 p.m. Eastern Standard Time, so the time here in Rochester. Just like for the midterms, I'll run a meeting in this same meeting room from 5:45 to 7:30 if people have questions. You can also send me emails with questions, and I'll try to sort of be on top of those in real time as those questions come in, so I can try to answer emails as well. If you have approved accommodations, we will adjust the time accordingly based on the accommodations approved by the university. And then also, so I'll put out a notification of this timing on the website right after class. And I'll also send out an email, and I'll be asking for people to let me know if they have a conflict with this exam time as soon as they can, so that we can reschedule the exam to a different time. So I've chosen the 14th here for two reasons. So first, because this is the last day that the university wants for us to input grades. But also, I think the other possibility I was thinking of was the 17th. But then that's getting pretty close to the start of the fall semester. So if people are moving, I didn't want to kind of interrupt that process. So that was my logic for picking the 14th here. But if you do have conflicts, or if for some reason that time doesn't work for you, please let me know, and we will try to work on something to find sort of a time that works for you. Does anybody have questions about the final exam? Okay, moving on. So we talked about, so here there's four sort of classes we'll have for review. So this Wednesday, this Friday, next Monday, and next Wednesday. So since the last exam, we've studied several different types of cycles. So we did Rankine cycles before, so you can add Rankine cycles in here. Particularly, I think Rankine cycles with regeneration tend to be one of the more difficult problem types that we do in this class, because this is kind of the one cycle we have where we split the mass flow. So conservation of mass becomes important here. Then we did internal combustion engines. So the Otto cycle and the diesel cycle. This is a picture of a diesel cycle right here, because we're adding heat at constant pressure. So we get some work out there. Then we talked about Brayton cycles. Here's a picture of a Brayton cycle with all the trimmings. So it's got intercooling, it's got reheating, and it's also got regeneration here. So knowing how to draw a TS diagram like this and analyze a cycle like this could be important. So we could go over a class like that, or a cycle like that. We talked about turbojet engines. Turbojet engines are the difficult part, I think, about the turbojet engine is the diffuser and the nozzle. So we have this kinetic energy part of the problem. So that's something that we don't see in other cycles. It's also a cycle where the working fluid is an ideal gas. So just like with internal combustion engines and Brayton cycles, it's important to be able to identify the isentropic processes here so that we can figure out when we're supposed to use the isentropic relationships. Finally, the last type of problem that we did was this refrigeration or heat pump cycle. So we're going to do an example of that problem today. Here, really, this is the same cycle. It looks like a Rankine cycle in reverse, but we have this expansion valve instead of a turbine. And then if we're a refrigeration cycle, we're interested in the heat coming into the evaporator, leaving our cold reservoir. And if it's a heat pump, like the example we'll do today, we're interested in the heat leaving our condenser, going into our hot reservoir. So I guess we have 4 students here today. So if one of you does anybody have a preference for what cycle type we talk about next class? Is there a type of cycle that you found maybe particularly difficult?
I would like to look at diesel cycles more.
Sure. So, Jack, do you mind? See, this is, I guess when you answer the question, you're also volunteering a little bit. So because I would like for the first time I see the problem to be when we get to class, so you guys can have the opportunity to see how I would solve the problem. So do you mind trying to find a sample diesel cycle type problem for next class?
That's fine.
Perfect. And then I thought someone else was unmuted there before Jack answered. Did someone else have a preference of a cycle?
Yeah, I was about to say diesel cycle as well.
Okay, perfect. So how about for next class, if Jack can bring us an example of a diesel cycle, then we'll work through that. And then on next class, we'll sort of pick an example problem that we'd like to do for the class after that, and someone can pick an example for that one. So we have 4 classes, and at least in this picture, this is not quite everything, but we have 5 different cycle types. So we'll be able to go through virtually everything. So if we can kind of go class by class and someone volunteers to find an example problem, then we can kind of work through the cycles that way. So for next class, I'll do a bit of a, how do you generally do cycles at the beginning, and then we'll go with a diesel cycle example problem. So with that, we'll move on to today's lecture. So today's lecture, we've been talking about these vapor compression, heat pumps, and refrigeration cycles, right? And I've been talking about how they're kind of like doing Rankine cycles in reverse. So the difference between a heat pump and a refrigeration cycle, if we're talking about vapor compression heat pumps and vapor compression refrigeration. So in both of these cases, it's like a Rankine cycle where we're moving back and forth across the vapor dome, but it's different than a Rankine cycle because the energy benefit and the energy cost are different, right? So in a heat pump, the energy benefit is this heat that's leaving our condenser that goes into our hot space. So the heat pump, the purpose is to heat up the hot space. So it's important for all of these cycles to be able to draw TS diagrams. So when we're drawing a TS diagram, one of the questions we have to ask ourselves is, what's the working fluid, right? Because if the working fluid is water or a refrigerant, then we need to know to draw a vapor dome, right? So that's what I've done here. I know that as I move through the condenser, I'm going to condense the fluid. So in this case, this is probably a little bit unreasonable for a real case, because you probably want your condenser to have saturated vapor over here. So your compressor, I'm sorry. So your compressor is compressing a vapor. But I wanted to have, when I drew this cycle the first time, I wanted to have one constant temperature in both of these things. So one constant temperature at rejection and one constant temperature at the heat transfer in. So here it's all under the vapor dome, which wouldn't necessarily be the case, right? But in our condenser, we're condensing our liquid till it gets to a saturated liquid. Then we move through the valve. Here in the valve, I've intentionally drawn this as a slanted line, so a line that's not vertical. And that's because I want to make sure that I notice that this is not an isentropic process. Remember, the assumption that we make when we go through the valve is that it's isenthalpic, which means that delta H is equal to 0. Then through my evaporator, I'm adding heat, right, which is evaporating some of my fluid. In a real system, we would probably want to go at least until we're all saturated vapor. And then my compressor, which is adding the power, would sort of move me over here to some higher pressure. So I'm adding work at the compressor. I'm rejecting heat through the condenser. I'm adding heat through the vapor, or through the evaporator. And over here, I've shown power coming out through the valve, because that's what would happen if this was a turbine, and we'd get that this power is m dot times delta H. But across the valve, delta H is equal to 0, so there is no power that's being generated as we go through this valve. You can think of this as just a thin copper tube, so as the fluid is going through that copper tube, it's losing pressure. So there is some pressure drop there. That's really all that valve does, and we make the assumption that it's isenthalpic. Right? Now, because this is a heat pump, we always have to think about what's the energy benefit and what's the energy cost. The only difference between a heat pump and a refrigerator, as long as they're vapor compression refrigeration and vapor compression heat pumps, the difference is what's the energy benefit. So in the heat pump, if we're drawing our little stick figure about where our sort of point of view is, we're over here on the hot side. We're interested in heating up this hot place, right? So the energy benefit is this Q dot on the hot side, which is Q dot from the condenser. For both heat pumps and refrigerators, the energy cost is the net power. And since the power from the valve is 0, the net power is the compressor power. So here, if we want to define our characterization parameter, because this is not a percentage value, it doesn't go between 0 and 100% or 0 and 1. We don't call it an efficiency. Instead, we call it a coefficient of performance. It's still energy benefit divided by energy cost. In a heat pump, the energy benefit is the heat transfer on the hot side, and the energy cost is the power required to run the heat pump. Remember, we got to plug this into the wall to run that compressor. Because the mass flow rate is the same for both the heat transfer on the hot side and for the power going in, we can make these little q dot divided by little w dot, which is just going to be delta H divided by delta H. We just got to make sure we get the right state numbers in there. We could, or a problem could ask us to compare our actual performance to our Carnot or our ideal performance. And if we wanted to find the Carnot performance, we would take T hot divided by T hot minus T cold. And we'd have to remember to do this using absolute temperatures, right? So this is either Kelvin or Rankine. So what do you do if you're lost? If you're on this kind of a problem, or really any kind of problem, you got to ask, so is it open or is it closed system processes as I'm going through my cycle? In this case, it's open system processes because the mass is moving through our cycle and different processes are happening in different components. So we got to say, where do we draw the control volume? What happens to the mass? So conservation of mass here, we're not splitting anything off. So conservation of mass is pretty straightforward. M dot in is always equal to M dot out. So there's only one mass flow rate in this problem. Then we got to say, what happens to the energy, right? So we could do the first law on each of these different components. And in an exam problem, we could ask you to demonstrate that certain processes were possible. So you could do a second law analysis to figure out if that sigma dot term was positive, because that's what we know for real processes. We're always generating entropy. Conservation of mass, hopefully this is no surprise. dm by dt is equal to the sum of m dot in minus the sum of m dot out. All components here will be at steady state. For each component, there's only one inlet and one outlet. So m dot in is always equal to m dot out. So there's only one mass flow rate in the problem. For each component, we'll write down the first law. Here I've written the first law down as if this is an imperial problem. Although in this case, we're going to neglect kinetic and potential energy for all of these processes. So it's different than a turbojet where we cared about kinetic energy for the nozzle and the diffuser. So even if this was an imperial problem and I missed the GC, I'm just going to cancel it out anyway. So at least I wouldn't get, I'd still be wrong, but I'd be wrong in a way that didn't impact my final answer. So here, assumptions that we might make include steady state, one inlet, one outlet. We'll always neglect kinetic and potential energy in these systems. We'll look at each process and say, is it adiabatic or is it passive? If it's a valve, we'll say it's isenthalpic, so it's adiabatic and passive, and then just H in is going to be equal to H out. Between the components, we'll say there's no friction losses and no heat losses in the system. If we cared about the second law, which is something that we might have to care about on the final exam, then we'd be interested in what happens to this sigma dot term over here. We know that if it's 0, that's not possible, but it's kind of the limit of what's possible, right? That's the ideal case. If it's negative, we know it's not possible, but if it's positive, then we know that the process can happen in real life. Here, if I'm dealing with the second law, the term that really, if I'm going to mess up, it's going to be this term. I get Q dot. This is the same Q dot that I would get for the first law, same sign convention. My T surroundings, this is the temperature not inside my control volume, but on the boundary, or failing that far away from my boundary on the outside. So this is the second law, and we'd be probably asking a question like, is it possible? And that depends on the value of sigma dot, or at least the sign of sigma dot, right? Then we'd get to some kind of algebraic expressions, right? Symbolic solutions. We might have to find things like delta H and delta S. So we'd have to ask, what's the fluid? If it's water or refrigerant, this is always a two-part question, right? But if it's water or a refrigerant, we'll have to say, well, is it subcooled liquid or a two-phase mixture or a superheated vapor? If it's an ideal gas, we'll have to say, well, am I going to solve this with constant specific heat or am I going to use variable specific heat, right? For delta H, for a heat pump problem, we might use one of these pH diagrams. We could use refrigerant tables in the textbook. We might have to use an ideal compressor. So if we were talking about a compressor that was ideal, we know that it's isentropic. But if it's a real compressor, first we find the isentropic outlet, and then we look to use the isentropic efficiency for the compressor. For the valve, we'll make the assumption that it's isenthalpic, right? I know these words can sound the same, but they mean something different. Isenthalpic means that delta H is equal to 0. So across that valve, H3 is equal to H4. There's also different methods for finding S. Again, we can use the pH diagram. We can use the textbooks. For ideal compressors, delta S is equal to 0. For an isenthalpic valve, delta S is not equal to 0, right? Isenthalpic means delta H is equal to 0. So I usually kind of exaggerate this when I draw it on a TS diagram so that this is more slanted than it probably would be if I was drawing it to scale. So we talked about this pH diagram, and this was something we only really introduced when we started to talk about this particular cycle. It's a scale drawing of a vapor dome. And this is if you were doing an FE exam. So as you get closer to graduation, if you'd like to get your engineering certification, then you want to be a PEng, then you have to write that test. And this is they won't give you tables for refrigerants. They'll give you a diagram like this, and you'll have to demonstrate that you can solve this graphically. So that's what we're going to do in the example today. We got to remember here that the enthalpy values here have a different 0 than the enthalpy values in our textbook. So we can't sort of do the problem half and half. We either have to do it all in the textbook, or we have to do it all on this graph. We can't split it half and half because they have a different value. You can't really do a problem half in absolute pressure and half in gauge pressure unless you're sort of converting between the two. So here is the example problem that I picked out. This is example 10.35 from the, I think, 8th edition of the textbook. So here we have this heat pump. We know that the high pressure is 200 psi, so heat rejection in the condenser happens at 200 psi. We're told that this Q dot out is 60,000 BTU per hour, right? So here we get some value here. It's not BTU per second, but we could convert that, or we can just leave it. We're told the temperature at state 2 is 180 degrees Fahrenheit. The temperature at state 3 is 110 degrees Fahrenheit, which makes sense. We're cooling the fluid down as we go through the condenser, and we're rejecting that heat into our hot reservoir. We go through this expansion valve until we get to a pressure where the temperature here at state 4 is 0 degrees Fahrenheit, right? This is the cold side, right? So this, in the evaporator, potentially we would, if we were under the vapor dome here, then we'll be under the vapor dome the whole time until we get to saturated vapor. And then we go through this compressor, increasing the pressure of that vapor until we get back up to state 2, where we're at 200 psi and 180 degrees Fahrenheit. So this is the information we're given for this particular process. We're asked to find the mass flow rate, the power consumed by the compressor, the efficiency of the compressor, so the isentropic efficiency of the compressor, and then also the coefficient of performance. And here, because it's a heat pump, this is gamma. If it's a refrigerator, it'd be beta. But if you just want to call it coefficient of performance, that's fine with me too on an exam. So what do? We always got two possibilities, right? We can start fixing states right away, or we can do the symbolic solutions. If you were, I know this is going to be the opposite of what I do, I think, in this particular example, but if you're working on an exam, particularly if you're pressed for time, I would get the symbolic solutions first, because I think that, if you think about a test as like a game where you're trying to maximize, points per time, I think that getting the symbolic solution gives you more points per time than fixing the states. But you can start fixing the states as well, because maybe you just feel more comfortable doing it that way. You can do it either way. So I think in this particular case, I'm going to fix all the states first, because fixing states on these graphs is something that we haven't done before, right? So here, this is kind of, I think, a nicer quality image of a pH diagram. So this is in the right unit system. So this is in imperial units. This is for R134A, so this is a particular refrigerant. We have pressure on the vertical axis. We have enthalpy, although really it's specific enthalpy here on the horizontal axis. Then there's all kinds of other stuff over here. So here are the constant entropy lines, the constant temperature lines, run like this. There's constant specific volume lines outside of the vapor dome. And we have quality lines inside the vapor dome. If you don't remember how to find the different lines or how to fix states using a graph like this, there is an example in the lecture that we did on Friday, which is posted on my YouTube channel. But we'll also go through and fix all the states for this problem here today, right? So here we know something about some states. So this is kind of weird because I'm going to start at state 2. So because at state 2, I was told 2 independent intensive properties. You could start at a couple of different places in this problem. You could start at state 1 as well. But here we know that at state 2, we have 200 psi. So over here, I go up my vertical axis. Remember, this is a log scale, right? So the distance between 20 and 40 is different than the distance between 40 and 60. And these kind of dotted lines are constant pressure lines. So 200 psi is about where this green line is. I think I missed it a little bit high here, right? Maybe you can see the dotted line there is a little bit below my green line. But that's the thing when you're doing graphical problems, you always sacrifice a bit of accuracy. The other thing we know here is that the temperature is 180 degrees Fahrenheit. So here I find the line, right? This is 100 Fahrenheit, 120, 40, 60, 80. So I follow this constant temperature line. I come over. So we get outside the vapor dome, and then we come down. And now our state point 2, right? Because we have 2 independent intensive properties. These lines meet only at one place on this graph. That means that we can fix our state 2 right here on the graph. So that's good. We've got one of our 5 state points that we need to find here, right? Now, maybe you only think it's 4, but I'll show you why we need 5 state points as we move through the problem. Then we know as we go through this process, as we go from state 2 to state 3, the pressure stays the same. Remember, we're rejecting heat here, so we're condensing our working fluid from a vapor down to a liquid. We move at 20 psi from 180 Fahrenheit down to 110 Fahrenheit. So here's 100, there's 120. I tried to pick a line that I thought was halfway in between here. This is vertically down. Where these two things intersect, that's going to be state point 3. So now I've got state 2 and I've got state 3. So what do I need next? I can go to state 4 next, at least if I think about what's going on here. So as I go between state 3 and state 4, I'm going through that isenthalpic valve. Now remember, isenthalpic means that H is not changing, right? So I am dropping my pressure, but they didn't tell me the pressure at state 4 or at state 1. Instead, they told me the temperature. So here, they said the temperature is 0 degrees Fahrenheit. So I follow this line down. And then, remember, temperature and pressure are dependent under the vapor dome. So here I have a horizontal line for this constant temperature. This is at about 20 psi. So I've gone down from 200 psi down to 20 psi. So an order of magnitude or a factor of 10. But now as I move through this valve, delta H is equal to 0, right? But H is here on this horizontal axis. So a constant enthalpy line is a vertical line. So I can just drop a vertical line down from state 3, and where it intersects this 0 Fahrenheit line, that's going to be state 4. Now I got state 2, I got state 3, I got state 4, I need state 1. So they told me state 1 was saturated vapor at 0 degrees Fahrenheit. So I got my 0 degrees Fahrenheit line. Saturated vapor is the same thing as quality equal to 1. So I'm right here at the rightmost edge of the vapor dome. So my state 1 is here. So with these 4 states, I can answer most of the problem, right? So I could tell you about the heat that gets rejected. I could tell you the power from the compressor. I could tell you the heat that gets added here on the evaporator side, but I couldn't tell you the compressor efficiency, because to find the compressor efficiency, I need to know how much power the real compressor consumes, but I also need to know how much power the ideal compressor assumes. So I need not just state 2, but I also need state 2s, right? The isentropic outlet, if we had an isentropic compressor. So for that to happen, I need to find a constant entropy line that goes from state 1 to state 2s. Now here, these entropy lines, I always find these ones are the trickiest to draw because the slopes, they're almost parallel, but they change a little bit, right? So here's one constant entropy line, and here's another constant entropy line, and I'm kind of in between those. So I'm going to draw a line that hopefully splits kind of those two constant entropy lines. This is this dashed blue line. This is my constant entropy line. And I'm going to put state 2s on my diagram here, and I'm going to make that an open circle, although it looks a little more like an ellipse. Maybe I squished it a little bit. That's going to be my state 2s, right? So here, right, this makes sense. If I went through the isentropic compressor, my specific entropy is less than if I went through the real compressor, right? Because these are constant entropy lines. I'm moving to the right as entropy or constant entropy increases, right? So now I have on my diagram state 1, state 2, state 2s, state 3, and state 4, right? Through the magic of PowerPoint, I'm going to kind of erase all these other lines, because what I want to do is I want to find the specific enthalpy values associated with each one of these states. Now the good news is state 3 and state 4 have the same entropy, or the same specific entropy. So I drop this vertical line down between state 3 and state 4. I'd already done this, so really I'm just extending this down to the x-axis here. This is a linear axis here in the horizontal axis. There's 40, there's 60. I gotta sort of graphically estimate this. If I was really trying to take my time, I'd maybe measure this with a ruler, how many millimeters between here and here, how many millimeters between here and here, and then I could kind of get a scale. But I'm going to say that, if this is 40, this is 60, 50 is kind of around here, and this is about halfway in between 40 and 50. So I'm going to call the specific entropy of H3 and H4 45 BTU per pound mass. It's not going to be right, This is every time we solve a problem graphically, we get the benefit of doing the problem faster, right? But there's a trade-off here, and the trade-off is that we're sacrificing accuracy, right? So I'm going to say that this is about 45 BTU. I can do a similar thing with state 1, drop a vertical line down here to find the specific enthalpy, right? This is going to be 100 BTU per pound mass, at least that's what I'm going to say here. State 2s, I'm going to say that this comes down at about 120 BTU per pound mass. And state 2 is going to be, I don't know, I feel like it's past 130. Maybe not halfway between what I'm thinking of 130 and 140. So I called this 133 BTU per pound mass. If you get an exam problem like this. So first, this is another argument. Again, I keep saying this, but few people do it. Use colored pencils, right? So if you get an exam problem like this, it's nice to be drawing different lines with different colors, so maybe they're easier to see at different times. I'm not really going to be grading your accuracy on the numbers that you pick off a table like this. Instead, what I will do is sort of grade your process. That's kind of always what I'm doing. Maybe if you mess up the math a little bit, you'll lose a point or two. But as long as you're kind of anywhere in the ballpark when you're reading these things graphically, that will be fine with me on an exam. So now we fixed all our states, right? So we can now go into the part where we would think about the symbolic solutions for the different parts of the problem, right? So first, I'm going to do the first law on the condenser, because I think the first thing it asked me for was about the mass flow rate, right? So if we're trying to find a mass flow rate, we want to look for maybe a component where it's adiabatic and passive. So maybe we have two different mass flow rates, but that's not the case in this problem. So instead, if we're trying to find a mass flow rate, we look for some place where maybe we know the power or we know the heat rate. And in this case, we know the heat rate, we know Q dot when we move through the condenser. So to try to find M dot, I'm going to do first law on the condenser. I'm going to say that it's at steady state, that it's one inlet and one outlet, that the change in the kinetic energy is 0, that the change in the potential energy is 0, that it's passive, that there's no friction losses so that this heat rejection happens at constant pressure, and I'll say that there's no heat loss in the lines throughout the system. Although I guess technically I didn't need to make that assumption in this case. Now, when I do that, I'll get this expression, which is the one that I'm expecting when I'm trying to find Q dot. This is Q dot from 2 to 3, that's through the condenser, is equal to M dot times H out minus H in. Now, in this case, I know Q dot, and I know H3 and H2 because I already fixed all the states. So the only thing I don't know here is M dot. Right? So here M dot is going to be big Q dot divided by H3 minus H2. The problem told me that 60,000 BTU per hour is rejected as I move through the condenser. This is heat out of my system because remember the system is inside the condenser and heat is leaving the condenser. So this is negative 60,000 BTU per hour. I fill in my values for H3 and H2 down here, right? So I'll get, and this is nice because I see H3 is less than H2. So this is what I'm expecting. I'm going to get a negative number in the denominator as well. And I'll find that I get 681.8 pounds mass per hour. I could turn this into pounds mass per second if I wanted to, but the problem just asked for the mass flow rate. I don't think they cared about the units, so I could probably put this in any unit that I like. Right? So if it was a test, I would just stop here unless they specifically asked me for an answer in something like pounds mass per second, and then I would change it. Next, they asked me for the power consumed by the compressor. Okay, so to do that, I'll do a first law analysis on the compressor. Right? So here it's at steady state, one inlet, one outlet, no kinetic or potential energy changes, it's adiabatic, no friction losses, and no heat losses between the lines, right? So we only have 4 states. I guess 5 if you consider 2s. So here I know that the power consumed by the compressor is going to be m dot times H1 minus H2. And because the compressor is consuming power, we know that the value here is going to be negative, right? So here we found m dot. It's like the problem asked us the parts in order for a reason, right? So we found m dot. I know H1 and I know H2. I see that H2 is bigger than H1, which makes sense because we're compressing our working fluid. We're putting energy into the fluid, and enthalpy is where it gets stored. So here we get negative 22,473 BTU per hour. And the problem, I don't think, asks us for a particular unit. So on a test, you could leave it like this. But if you went to Home Depot or something and asked for a compressor with a power of 22,473 BTU per hour, you might not find somebody who can help you, right? So we might want to convert this into horsepower. And if we do, we would look on some kind of equation sheet. We would see that the conversion factor to get from BTU per hour to horsepower, here we have to divide by 2,545. It's a nice round number because we're dealing with the imperial system here. And we see that the power of the compressor is 8.83 horsepower. So that's good. Now we found part B, right? The next thing the problem asked us for was, how do we find the isentropic efficiency of the compressor? Now, we know that the compressor, the energy here is a cost. So we know that if we were looking at the ideal compressor, we would pay less, right? The cost would be less. So here we put the ideal compressor on top of the real compressor. Now, if we were doing this problem beforehand and we didn't realize that we had to get H2S, that would become apparent when we did the symbolic solution here. So this is actually an argument for doing the problem in the opposite order that I did it in this example. So if we did the symbolic solution first, then the symbolic solutions would tell me the variables that I need to find in order to fix the states, right? So I guess I had to use my engineering intuition when I was fixing the states to know to look for H2S. But if I didn't know that, I would get to this point in the problem and say, oh, I got to go back to my diagram and find the isentropic outlet for the compressor. But I've already done that. So I have these values. I get negative 20 on the top and negative 33 on the bottom. So my compressor efficiency is just over 60%. Finally, I'm asked to find the coefficient of performance. So I want to characterize how well the whole cycle does. So here, my coefficient of performance, because this is a heat pump, I use the Greek letter gamma. But here I divide the energy effect, the energy benefit divided by the energy cost. That's what I do in all of these cycles. The energy benefit is the heat transfer rate on the hot side, and the cost is the net power. So if I wanted to factor out the mass flow rates, I could also look at little q dot divided by little w dot. But here I actually already have big Q dot and big W dot, right? So here in this problem, I've sort of broken this down. The problem told me right away what Q dot on the hot side was. So I wouldn't do any math. I wouldn't use any thermodynamics to find this value because the problem just told me this number. I've already found this is the power consumed by the compressor. In my equation for net power, I've also included the valve power here. But we know that the valve power is going to be m dot times h in minus h out of the valve. But delta H across the valve is 0. So this valve power is going to be 0. Right? And I think part B of this problem was what's the power consumed by the compressor. So I wouldn't work this out again. I've already found that answer. So here, the heat transfer rate is negative 60,000 BTU per hour. And the power consumed by the compressor is 22,473 BTU per hour. That's also the net power because the valve doesn't consume any power. So here I get a coefficient of performance of 2.67. So if this was a refrigerator or an air conditioner, we'd have to take the absolute value of this coefficient of performance because these coefficients of performance, they're always positive, right? If you think about this from a marketing perspective, you know, nobody wants to talk about how a refrigerator has a coefficient of performance of like negative 12 or something, right? Like that sounds bad. It would probably be pretty good, right? So these coefficients of performance are always positive, but for a heat pump, it doesn't really matter because you have a negative divided by a negative. So that's the end of the lecture today, and it's actually the end of all the new material. So what we're going to look at on the final exam is cycles. So we can only ask you, or I can only ask you 3 long answer problems on different cycles. So you could expect, you know, from our picture before, maybe there's 5 different cycles. The multiple choice questions will sort of deal with some other cycles that we don't cover in the long answer portion. And I guess, I don't think we saw this on the midterms, but for the multiple choice questions, we'll also have some groupings. So I may give you maybe a diagram of a cycle. Maybe it's a TS diagram or a PV diagram or a diagram of different components in a cycle, and then ask you, or a state table maybe, and ask you a series of questions about that, right? So you might get some, you know, a picture or some information, and then say, oh, the next 3 questions will be to do with this picture. And I guess that means on a multiple choice that's run through my courses, you might get that same picture multiple times. But when we do that, or when I do that, I'll be careful to make sure that none of the, so there, let's say you got a picture, you know, a Rankine regeneration problem, and I asked you questions about it in the multiple choice, and there's 3 questions. None of those questions would be dependent on an answer from a previous question. So you won't be in a case where, if you got question 4 wrong, then you're also going to get question 5 or 6 wrong. So they'll all be sort of independent. So, you know, if you make a mistake on one, you won't, that mistake won't carry through. So I'm happy to, in the 5 or 10 minutes we got left, I'm happy to field any questions that you have about either the example that we did today or the final exam coming up in just about 2 weeks.
Would the questions on the exam that aren't about, that are about, cycles, would they be similar to ones we have on quizzes where it's like they ask us facts about the cycle, like what common assumptions are made about this kind of a cycle or not made about that kind of a cycle, or would they be more application problems?
So I think just like in the midterms, I'll probably shoot for a distribution of about 50% problems where you're doing math and 50% problems where you're doing kind of definitional stuff.
Okay, thank you.
You're welcome. Any other questions before we end it for today? All right. Well, thank you very much. Jack, remember to bring us a diesel problem for next class, and we'll kind of struggle through it together. Thanks, everyone.
Thank you.